Hey guys, welcome back. Today we're going to be talking about soils. Are one of those really cool topics in geology that unfortunately we don't spend enough time on, if you ask me. There's a whole science behind soil formation, and it's basically an offshoot of erosion and diagenesis, things that we're going to be talking about from the past lecture, this one, and into the next one when we get into full-on sedimentary rocks. So with that said, let's go ahead and actually describe what soils are, get through the science a little bit, and find out why they are in fact so cool. Okay? Well, soil is a combination of mineral and organic matter, water, and air. If you remember from one of the earlier lectures, we talked about how there was the hydrosphere, the geosphere, the atmosphere, and the hydrosphere all coming together. And interacting. And the place where they do the best interacting and create kind of the optimal conditions is actually right in soils. Okay, so here we see a typical cutout of subsoils, and we'll notice that it almost looks like it has these layers in here. And we'll actually describe what these layers are. They're very, very neat, and it actually turns out that the science behind them is pretty straightforward. You'll be able to understand it by the end of this class. You'll look at this and be able to recognize instantly what is happening here in this picture. As a matter of fact, we might actually come back to this picture at some point because it's just such a good one. So anyways, that portion of the regolith, here's a nice little vocabulary word that I want to make sure that you know. Regolith, which is rock and mineral fragments produced by weathering. Okay, so it's busted up rock from weathering that supports the growth of plants. Okay. Remember, I was talking about those four spheres. Here we see them again. So this is typical components of soil that yield good plant growth. This is what you want. It turns out that soil is about 45% minerals. So less than half of it is actually mineral matter. About 5% is organic matter, bacteria, decaying roots, maybe some moss, things like this. And of course, there's water. Believe it or not, there's actually water in the soil at all times. Good soil is going to have about 25% water in there. And then the rest of it's going to be open air space. There's going to be some good air transfer that's going to be moving between the roots and the surface of the air. So basically, the soil will be, in a sense, kind of breathing, if you will. 25% air volume. Okay? It's kind of hard to believe that there's that much air in soil, but there in fact is. All right, so there's several factors that you need to be aware of when we're going forward. So, like I said, the science of soils is very complicated. We could spend an entire lecture just dealing with parent material, another one on time, another one on climate, another one on plants and animals, another one on slope. But we're just going to go ahead and just buzz through it here in this lecture, and unfortunately, that's the amount of time that we're going to have in the class on it. So there's lots of books, by the way, you can read up on this. But anyways, parent materials. This could be residual soil. This is the old stuff that was there before. Parent material is the underlying bedrock. So right there, maybe the soil is forming from the rock that it's actually sitting on top of. Another way is transported soil, right? Sometimes soil comes in from somewhere else. This forms in place on parent material that has been carried from elsewhere and deposited. All right, time, of course, is important in all geologic processes, and the amount of time for soil formation varies for different soils depending on geologic and climatic conditions. So geologic, remember, certain minerals tend to break down very easily, such as your calcium plagioclase, but things like quartz do not. And then, of course, climatic conditions are also going to be very big. Climate, which is probably the most influential control on soil formation. Many key factors are temperature and precipitation. As a matter of fact, these are probably the two most important factors for determining what kind of soils are going to form. Okay, plants and animals have a huge role to play. Of course, the organisms influence the soil's physical and chemical properties, and they also furnish organic material to the soil. And then, of course, steep slopes have poorly developed soils, right? Because whenever the water comes, it washes it right off. And the optimal terrain is a flat to undulating upland surface. You can kind of think of the Great Plains of the United States, of North America that way. There's also areas in Central Asia that are also quite good in this matter. So here we can kind of see the three general areas where we can see where soil will tend to develop, but sometimes it will last and sometimes it won't. So here we see soil is going to form. Here's a cross section here in the river valley and these cliffs, and this is an image of some cliffs here. You're not going to get a whole lot of soil development because of the steep slope, right? There's nothing much is actually going to form here. You get some, but not much. Okay. And the reason why is every time it rains, it just washes it right down into the valley. All right, so this all gets transported down into the valley where the river is. And that's going to put us onto a transported soil. Remember, this is transported, which is material that was brought in from somewhere else. And here we can see these unconsolidated deposits down here at the bottom of the river. The river is kind of working its way through here. And this, it turns out, is actually a really great place to grow a lot of things that require a lot of water, I should say. The problem, of course, of growing crops in here is that tends to flood and wipe out your crops from time to time. Okay, and then of course, probably the best place are the residual soils that is developed right on the bedrock. So over here we see thick soil that will tend to form right on the bedrock. Here we're getting a little thinner soil because it's going to be on a slight slope. Here there's none, and here's quite thick horizons of soil, and of course you get horizons of soil in here as well. Okay, so the way that this comes about, it turns out that there's a process behind it. Now, it becomes actually pretty obvious that there's a process when you look at the very first picture. This did not form from a magma chamber in this way. This had to have occurred over time, and in fact it did. And this is a pretty typical set of horizons that we see. First off, you got basically a topsoil and a subsoil. The topsoil gets, there's two kinds of important things that we need to keep in mind here. There's the organic matter up here at the top. In this case, it's going to be the grass and the tree. So anything that falls out of the tree, like the leaves, will become part of that organic matter. And that's what we call the O horizon, right? So these vertical differences are called horizons. The A horizon is the organic matter mixed with mineral material. And sitting above, sitting below the O and the A horizon is this E horizon, leaching by downward percolating water. So you're going to have a lot of water working its way through these plants. It's actually going to pick up a little bit of acid while it goes through these plants for some sophisticated reasons. And basically that acid is going to strip out a lot of the nutrients and percolate things down, especially clay minerals and iron oxides and calcite, things like this. And so we would actually tend to see an area here that is lacking a lot of minerals that would be discolored, usually to a lighter color. So let's go back to that original photograph back here. And here you can see it, right? Here's that horizon over here. So here's our A horizon. Here's our O horizon, this grassy material up here, okay? So that leaching area is called the E horizon. Now, sitting above the E horizon, sitting below the E horizon is the subsoil. So everything below this light-colored section is the subsoil, and this is where you get a lot of that percolation is washing a lot of the clay minerals and iron oxides and calcite down lower, and this is basically where the rock is being broken up over time. In this case, the roots are helping break it up, but they're breaking up the unweathered parent material, or actually the rocky material. So again, let's go back to this original one. Here we can still see the rocky material still in the soil. It's still breaking it up over time. But here you can see it clearly. Here we've got an O horizon, A horizon, an E horizon, and then everything down here is going to be the B horizon. This is it's actually the zone of accumulation. So the stuff that was in here is washing down into this tanner area down here. Okay. And then, of course, the C horizon, the material right on top of the bedrock that's breaking up, and then the bedrock itself. And so this would be an example of exactly what we were describing. Here we have the O horizon up here on top, a very nice and well-developed A horizon. And sitting right below it is this patch. This is a mollisol, by the way, in coastal Oregon. Mollisol is a soil that forms in grassy areas. And so here we see an area of leaching very clearly right in here, okay? Really nice horizons in here. We're not going to get into the nuances of this, but here you can actually start kind of detecting that there is some soil material that's actually sloughed off the top here. So don't think that this is bedrock material down here. Okay, this just fell off this cliff. Here's another set of horizons. You can actually tell this one right away. This is what they call a paleosol, which means an ancient soil. It's very, very old, and this is from a trench that was dug in the United Kingdom. And here we can see again, here's the O horizon, here's the A horizon. So this is that really good zone of good productive soil right here on the top. This is where all the organic accumulation is, that nice A horizon. Notice it's not very thick here. Because right below it is the E horizon. So the E horizon here, and unfortunately we don't have a tape measure, but this is probably about 4 inches thick, sitting on with 6 inches of A horizon on top of it. So it's not a real thick horizon. And then below it, going all the way down, and unfortunately we can't actually see the C horizon, but this is all B horizon material. We can actually see some busted up material in here. So this might actually technically, we might be able to start calling a C horizon in here if we wanted. But anyway, here you can clearly see the different units of soil development occurring. All right, so it turns out there's different ways to characterize soils and describe them. Soil texture is one of the best ways to do this. So usually you could take the amount of clay and the amount of silt and the amount of sand, and you could put on a little chart. You might be, especially those of you that are only experienced in the humanities and looking at the way charts are developed there, it's pretty uncommon in the humanities to see what they call a ternary chart. In sciences, it's actually fairly common. So let's go ahead and get acclimated to how to read one of these. So in this case, we see that it's a triangle or a ternary diagram. And if we wanted to know something that was 50%, I'm sorry, 30, 30, 33%, 33%, 33%. In other words, 1/3 silt, 1/3 sand, and 1/3 clay. So this would be the clay up here. This would be the sand down here, the silt right here. That'd make it all evenly distributed, right? So we would go to some point out here, right about here, matching out over here, and that would put us right in the middle of our ternary diagram. That'd be a clay loam. So a loam is actually a kind of soil that has a combination of sand and silt in here. So pure silt, if it's got a little bit of sand in it, it becomes a silt loam. If it becomes 50-50, it's actually a loam. And so this is a word that is used by soil scientists all the time. If it's just mostly clay, even if it has a little bit of silt and sand, the clay actually dominates the texture. And, clay is kind of sticky. It tends to, you can ball it up and do all kinds of interesting things with clays. So anyways, here would be the clay sector, and it kind of dominates this whole apex of this ternary diagram. So anyways, if you know the amount of material you have, silt, sand, and clay, you can go ahead and describe it as one of these textures, silty clay, sandy clay loam, or whatever. And every soil scientist in the world would be able to look at this chart and know exactly what it is that you're trying to describe. Another way that they kind of describe these things is through something called soil taxonomy. This is very similar to how they classify organisms, right? Organisms are, they have a kingdom, phylum, and all the way down to species. Soils kind of do the same thing. And they all start with kind of 12 major orders way up at the top. And this is an image taken from the the Natural Resource Conservation Service of the USDA. You can actually get this, I believe, for free from almost any USDA office. And anyways, it's a picture of the 12 major orders of soil. So, here's your andesols and iridosols and entosols, and we'll describe what all these things mean. But anyways, these are nice images of what they are. And if you get one of these charts, which you should be able to get online, if you choose to get one, it will describe what these soils actually mean. But we're going to give kind of a brief introduction to at least a couple of them right now. So soil taxonomy is really the way that soils develop, right? So here we actually see the different kinds of soils, entosols, and over on the other side are oxasols, another group called the mollisols, which we described earlier, and iridosols. What are they? So an entisol is just a soil that's being developed basically right now. This is a recent soil. And basically you take this entisol and you begin to exact chemical weathering processes on it. Now, depending on the climate, you're going to get different kinds of processes occurring. For example, in a permafrost environment, you're going to get something very different than what you're going to get in a rainforest. So here we have an entisol. It's recent, and if we put it, for example, into that permafrost, it follows this track right here, it'll form a soil called a gelisol. All right, this is very cold. And how much weathering and soil development occurs? Well, it's just slight, it turns out, right? Because if you can recall from our discussion on weathering patterns, you need to have a lot of high temperatures. You actually have to have higher temperatures to get good chemical weathering. Otherwise, you only get slight chemical weathering and mostly physical weathering. So it turns out permafrost tends to generate gelisols. Well, what if we get strong weathering, like what we see over here? Well, that would be the oxisols. And we find that occurring, of course, in wet tropical rainforests. We get extreme weathering. Don't worry about the clays and iron oxide stuff, but you'll see that oxisols tend to form here. And this is a very, very stripped out, it's well developed, but all the nutrients are stripped out. And this is what we find in tropical rainforests. We'll come back to why this is important for ecological purposes later on. Mollisols, this is kind of in the intermediate. These are usually in grasslands, semi-arid to moist. So it's right in the middle here. Alpha sols, of course, the same thing. On the other side here, where it's mostly mildly acidic clay accumulation, right here. Okay, so you kind of get the idea how these kind of arise from the development of diagenesis and the breakdown of igneous rocks and even metamorphic and sedimentary rocks to form soils. So here we see these global regions where all these 12 soils exist, right? Here are the alpha sols, they come up a certain color, and andisols. Let's go to the ones I brought up, right? The gelisols, I just said these tend to form in cold environments. Well, it turns out here are the gelisols up here at the northern part of Alaska, into the Klondike region of northern Canada, all the way up into the areas just to the west of Greenland. And then back over here, this is Siberia, into northern Russia, the Kola Peninsula, and even down into the Moscow area. Very cold area. Very, very, very cold area. And you get really nice gelisol development in these areas. And so the types of plants that grow on gelisols tend to grow in these areas. Okay, alternatively, remember we're talking about oxisols. Oxisols are these areas of extremely high chemical weathering. Remember this right here, way over here. We come back to our map and look, we see oxisols was pink. Here's that pink color right through here. This is the Amazon rainforest. Here we actually find the same kind of forest environment here. We'll find little patches of pink in here, but you'll notice it's all kind of at the same latitude moving through here. It's the tropics. All right, we get oxisols. What about some of the best places for pasture land, the best grass? Well, those would form on mollisols, right, the grassland. And sure enough, we've got mollisols that form over here in eastern Argentina, southwestern Brazil. But most famously, notice the grasslands here in the United States, all the way up into southern Canada. This is the famous food growing areas, Iowa and Kansas. And then, of course, over here would be northern China and southern Mongolia. We have beautiful grasslands that extend literally all the way to eastern Europe. These grasslands here were conquered by Genghis Khan, and we see a very strong influence of Asian culture that came in along these grasslands because of the ability of these people to transport goods and services and to cultivate them very easily. All right, so this is fantastic. This is basically the bread belt of Russia, and here's the bread belt of the United States, and of course of South America. You can see pretty rapidly why understanding soils is so important to your understanding how your economy actually works, right? You would want to know something about how an ultrasol works if you're living in the southeast. If you're in an aridisol, this is a desert climate, a desert soil. Well, that's over here on the other side. So anyways, you kind of get the idea. All right, so beyond that, we can actually start to differentiate more than just an an ultrasol or an aridisol or an oxisol or a paleosol. Turns out that the soil taxonomy then breaks down to, okay, you have an oxisol. What kind of oxisol? And so there's suborders, bunches and bunches of them based upon moisture regime and mineralogy. Then that can get subdivided again to diagnostic horizons, whether they exist or don't, subgroups beyond that, and you get the idea. And so ultimately you can get to a series, and that means you have about 13,000 different soils that have been categorized just so far. And probably by the time the human species is done categorizing soils, we'll probably find 5-6 times that. Who knows? It depends on how much we want to split that argument up. So it turns out that you can do serious damage to your soils. Your soils are a resource. They are relatively finite. The earth is constantly remaking them. But in some areas for example, in Hawaii, you're able to generate new soils within about 80 to 100 years. That's still about a human lifetime. But if you're in an arid area, such as in Sudan, soil development could take centuries. It could actually take more than centuries. It could take millennia. All right. So in this case, this is actually a picture of Sudan. Let's go ahead and read through here. The agricultural productivity of soils can be improved through fertilization and irrigation. That's what these guys are trying to do. So here we have a field. This is a degraded soil, and they're basically trying to treat it. They're trying to save this field. And the soils can be damaged or destroyed by careless activities. The problem with damaging your soils is that this is crucial for providing food, fiber, and other basic materials. Fiber being things for paper, and of course, it is one of the most abused resources. We take it for granted all the time that it's there. Here in Sudan, this is actually an old plantation, and the plantation, of course, doesn't look like a plantation anymore. At one time, the soil was much higher. You can see this kind of puffed up area, or this area that looks like it's pushed up. It's not actually pushed up, it's that everything else is washed away, and this has been left high. This is the old E horizon. The A horizon here has been completely stripped off. And so what they're trying to do is they're actually trying to use tractors and whatever to try to rip up the B horizon and to try to force it to be productive. You can tell they're not terribly successful in doing this at this time. All right, so clearing the rainforest, it turns out, has an amazingly bad effect for rainforests, I should say. So let's look at this human activity. First off, we see that this bulldozer is clearing it out. The soil is this orange color. It's not black. It doesn't have a whole lot of organic material. And the reason why is, and we've talked about this, the reason why I picked this as an example, is because we are dealing here with wet tropical forests. These are oxisols. So in other words, there's a lot of iron and aluminum oxides in the soil. The soil does not have a lot of organic material. It's very strongly developed, but not a whole lot of organic material. It turns out that rainforests sustain themselves by recycling that O horizon very efficiently. So let's come back to this. So here we could see, here's the O horizon, which of course is the forest, and right below it, we're basically straight into the oxisol. There's almost no nutrients here. The rainforest is recycling carbon like crazy right here. And when you strip this thing out, you're actually removing the O horizon. What can grow here after that? Nothing. And observation of areas where they've tried to rehabilitate these rainforests show that they don't actually rehabilitate the rainforest itself. It turns into a grassland, and in some cases it actually turns into a desert. So this is really a bad way to kind of clear land. A lot of these rainforests have been in existence since 100 million years, especially in the Brazilian, the Amazon rainforest. Okay. So that's in fact what this says. Soils in tropical forests are poor in nutrients and unsuitable for agriculture. You cannot grow things here. This is really a bad way to treat. You cannot grow corn on this. Most of the nutrients in tropical rainforests are found in the trees. And so sometimes they burn the trees and then try to force the ashes into the soil. That's not really a very good way of doing it either. And of course, clearing soil or clearing the tropical rainforest also promotes soil erosion. So it just makes the whole thing, it's a bad situation all around. It's really not the way to go. All right, so here we actually see a field. There's a couple of people here, or there's a person standing here and a person standing here, and between them you can see this field is being deeply eroded. This is recent erosion. The reason why we know it's recent erosion is because if it was ancient erosion, we'd have deep gullies here. This has just occurred recently. So this is where a farmer has come through and cleared his field. Unfortunately, by doing so, he's removed, and I'm assuming it's a him, removed basically what erosion control existed naturally, which was probably some native plants that were there at the time. By removing that and putting his own, agricultural product, whatever this may be, grass or alfalfa or whatever it is, it wasn't able to stop the rain, and the rain was able to start washing it away. So here it ripped it up, and here it's deposited it down here. Not necessarily a good situation. I've actually heard farmers refer to this kind of erosion as cancer of the land. It's a real bad phenomenon, especially if it happens over long periods of time. So erosion rates are dependent on climate, slope, and type of vegetation. Human activities such as deforestation and farming practices can enhance soil erosion. That's what's being demonstrated right here. All right, so let's talk about some of the byproducts of the weathering and the formation of soils. So weathering creates deposits by concentrating metals into economically valuable concentrations. This is called secondary enrichment. Remember those oxasols. I like oxasols because it's probably the easiest one to conceptualize. Remember that nice red color that soil was? That soil was turning red because everything was being leached out of it, but iron and aluminum oxides were being retained and even in some cases concentrated. And so you get a mineral or a rock called bauxite. It's actually a mineral. And it's the principal ore of aluminum. It's aluminum oxide. And it's found in rainy tropical climates from chemical weathering and the removal of undesirable elements by leaching, right? So this is right out of what you would consider the E horizon. And this is where we get our aluminum from to make all of our aluminum products. There are other sources of aluminum as well. Bauxite is the most economical way to do it. Okay, so it turns out that not only are you producing bauxite, but soils actually produce some other really cool byproducts and ore deposits that are really useful to us. For example, copper and silver are frequently deposited in this way, not always perfectly into the soils, but as a byproduct of the weathering and formation of soils. So, these typically occurs in deposits containing pyrite, where you get the copper and the silver. They tend to go hand in hand. But here we see, this is copper carbonate right here. This is two different minerals. This is azurite, this is copper carbonate, and this is copper carbonate. Notice that copper, when it's combined with a carbon, or with carbonate actually, forms these beautiful blue colors. And so this is a product of weathering, and this is copper ore. This is where we get most of our copper wiring from, is from minerals that look like this. Pretty interesting stuff. Malachite and azurite, under a microscope, it's a really beautiful mineral to look at. All right, so I hope you enjoyed this little lecture. I know that we kind of went through it pretty quick. Soils, like I said, there's a whole science to it. I mean, you can go through an entire class on each one of those orders that we were talking about, an oxasol, an alphasol, and you name it. And we just kind of breeze through it. But if you have an interest in this, usually most colleges and universities offer soil science courses right there on campus, where they deal with, for the entire semester-long subject of soils and their formation. So anyways, just thought I would throw that out there. Anyways, if you have any questions, or there's something that you need cleared up that you didn't understand from this lecture, feel free to send me an email or meet me on the discussion boards. Until next time, have a good one.